giving me this opportunity. To speak here. So I will talk about an uncertainty principle for certain eigenfunction expansions. So let's start with the word uncertainty principle. I think it was best explained by Folland, where he said the uncertainty principle is partly a description of a characteristic feature of quantum mechanical systems, partly a statement about the limitations of one's ability to perform measurements on a system without disturbing it, and partly a meta theorem in harmonic analysis that can be summarized as follows. A non-zero function and its Fourier transform cannot both be sharply localized. So in more simple terms, uncertainty principle says a function and its Fourier transform, which is defined by this prescription, cannot both be small simultaneously. And depending on different notions of smallness, we can get different uncertainty principle. So for example, among several avatars of uncertainty principles, so the most famous one by Hardy, where Hardy proved if the function and the Fourier transform both decays like Gaussian. So the function is of order e power minus mod x square, and the Fourier transform is also of order e power minus b mod xi square. Then depending on a and b, that is when ab is bigger than 1/4, then the function is 0. So that's sort of a notion of smallness, which is given to the function side and the Fourier transform side, and which is a well-known uncertainty principle. Now let's move to a different kind of smallness. Let f is an integrable function, and its Fourier transform has exponential decay. Then using the inversion formula, we can actually extend the Fourier transform to a tube domain by just putting the IUI here. The IUI will go in the exponential factor, so everything makes sense. And as long as we are in the tube domain, we can use Morera's theorem to prove that this is a holomorphic function. Now, since a holomorphic function, then it cannot, if it vanishes on an open set, then the function will be 0 by identity theorem. Now you can see that, so here two different kind of smallness. For example, one on the function side, it is vanishing on the open set. Another on the Fourier transform side, it has exponential decay, give rise to a elementary uncertainty principle, which was easy. Now the question is it possible to arrive at a similar conclusion with a slower decay on the Fourier transform side? That is, suppose the function vanishes on an open set and the Fourier transform has this kind of decay. You see this kind of decay where the Fourier transform is decays like e power minus mod xi by log of 1 plus mod xi. This is certainly slower than the exponential decay. Equivalently, one can also ask for a non-trivial function f which vanishes on an open set, what would be the best possible decay admissible for its Fourier transform? So this was first in 1934. This was first answered by Ingham. He proved that if theta is a decreasing function vanishing at infinity, and suppose f is a integrable function whose Fourier transform has this kind of decay, where the Fourier transform has e power minus theta mod xi times mod xi. You can see since theta is decreasing, so this is certainly slower than the exponential decay. Then depending on the behavior of theta, there is an uncertainty principle which was proved by Ingham. So he proved if the theta is not integrable with respect to the measure T inverse gt and f vanishes on an open set on R, then f is 0. Moreover, this condition is sharp in the sense that if theta is integrable with respect to the same measure, then there exists actually a compactly supported smooth function whose Fourier transform has that kind of decay. In fact, the Ingham used the classical Denjoy-Kahneman theorem for quasi-analytic functions to prove this kind of results. And also the example that Ingham constructed is very crucial in proving Ingham type result, because it not only proves the sharpness of the result, but also it is used to prove the first part of this result. So this is the uncertainty principle we are interested in. So instead of using Denjoy-Kahneman theorem, another way of proving this type of problem is to use a theorem of Chernow about quasi-analytic function. So we'll state that first. So Chernow's theorem says if f is a smooth function on Rn and delta is the standard Laplacian on Rn. Suppose all the powers of Laplacian applied to f is in L2 and they satisfies this condition that the series is divergent. This we often called Carl-Lemon condition. So if that thing satisfies this Carl-Lemon condition, then if f and all its partial derivatives vanish at a single point, any point, then f is identically 0. So this was the theorem of Chernoff, and this can be viewed as a L2 version of Denjoy-Carl-Lemon theorem, and this turns out to be very useful in proving Ingham type theorems. So this actually provides a sufficient condition for a smooth function to be quasi-analytic. And again, one remark is that to prove Ingham's theorem, the full power of Chernoff's theorem is not required. Only a stronger vanishing condition. If I replace this vanishing condition, f and all its partial derivative vanishes at single point. If I replace this by a stronger vanishing condition that f vanishes on an open set, that is also enough for our purpose. If I want to prove the Ingham theorem only. Now, because of this beautiful nature of this theorem, it is also natural to ask: are there operators other than Laplacian which generate we generate this kind of quasi-analytic class? I mean, analog of Chernoff's theorem for operators other than Laplacian, for example, are there elliptic operators? So this kind of questions, that is Ingham's theorem and proving analog of Ingham's theorem and Chernoff's theorem, has received considerable attention in recent years. So before jumping into the main part of this talk, I will just want to quickly review the recent progress in these topics. So it was first generalized in the higher dimensional case, higher dimensional Euclidean space and torus by Bhaumik, Ray and Sen. So they actually considered the n-dimensional Fourier transform, and they proved Ingham's theorem. They used a several variable version of Denjoy-Carl-Lemon theorem in this proof, and they proved the existence of that example at the sharpness of the theorem by using some Radon transform technique and original example on Ingham. Next, Bhaumik and Sen considered the case of complex semi-simple Lie group, where they proved an Ingham's type theorem for the ky invariant functions. Later, Bhaumik, Pusti and Ray, they considered the setting of Riemannian symmetric spaces of non-compact type. So on that space, they first proved a Chernoff's theorem. So it's a Chernoff's theorem for the Laplace-Beltrami operator on that space, but with a stronger vanishing condition, because their main aim was to prove Ingham's theorem. So the stronger condition was f vanishes on an open set. So with that stronger condition, they prove a weaker version of Chernoff's theorem and use that to prove an Ingham type theorem. Again, in the example case, they used the Euclidean example to construct an example on the they use some Abel transform technique to construct an example for the Ingham's theorem and on the Riemannian symmetric space of non-compact type. Later, we also got interested in this kind of result. So in a joint work with Bakchi, Sarkar and Thangavelu, we considered the case of Heisenberg group, and there we proved the Chernoff's theorem for the sublaplacian with a exact vanishing condition, but the function, there is a restriction on the function. We have only able to prove the theorem for Korani radial functions, and the functions only vanishing at a single point, but and that is a specific single point, that is 0. So still there is an open problem for Chernoff's theorem for the sublaplacian, and also we use that to prove an Ingham's theorem, but here the example cannot be deduced from the Euclidean example. So there is we have constructed a very non-trivial example. Okay, so I will discuss that in this talk later.
So what are Korani radial functions?
So on the Heisenberg group, there is a homogeneous norm, right? Korani norm. So the functions which depends only on that norm. It is not the usual radial, that is Heisenberg radial depends on mod z.
Yeah,
it is not just mod z, it is just mod of z comma t, depend on that.
Okay, fine. Yeah.
So moving on, then Bhaumik, Parui and Pusti, they considered the case of Fourier-Dunkel transform on the for Ingham theorem. They actually proved the Ingham's theorem for the Fourier-Dunkel transform. Later, we considered the case of rank-on Riemannian symmetric space of non-compact type. And there we considered the case of generalized spectral projections associated to the Laplace-Beltrami operator. And we proved the Ingham type theorem for this. And this is actually a sharper version of Ingham type theorem. Actually, as a corollary, one can get a theorem for the Helgason Fourier transform. In the same paper, also we considered the generalized spectral projections for projections associated to Laplacian on Rn and Dunkel Laplacian. Then we proved Chernov's theorem and Ingham's theorem for the rank-on compact symmetric space, special Hermite and Hermite expansions. So basically we proved Chernov's theorem, but with the stronger vanishing condition where the function vanishes on open set for the Laplace-Beltrami operator on rank-on compact symmetric space, Hermite operator and special Hermite operator, and use that thing to prove. Then we using that we prove Ingham type uncertainty principle for the spectral projections associated to those elliptic operators. And then Bhaumik, Pusti and Ray revisited the Riemannian symmetric space case of non-compact and compact type both, and they proved Chernov's theorem for with a genuine vanishing condition, exactly same as the Chernow vanishing condition, that is function and its certain derivatives vanish at a single point, but they got a restriction in their function. They only proved the result for the k by invariant functions. Then we also considered the rank-on Riemannian symmetric space, both compact and non-compact type, and proved a genuine analog of Chernov's theorem in a joint work with Manna and Thangavelu. So here we considered a function and its derivative vanish at a certain.
This result was for IMRN result for any arbitrary rank, right?
Yeah, there is no restriction on the rank.
Yeah. That's right.
But in our case, there is a restriction on the rank, but there is no restriction on the class of function. So yeah, now recently we revisited the Heisenberg group in a joint work with Thangavelu. We revisited the Heisenberg group and we proved the Chernov's theorem, where there is no restriction on the function side, but we used the stronger vanishing condition. It is f vanishes on an open set, and we got a Chernov's theorem for the full Laplacian. And we used that Chernov's theorem to prove Ingham type theorems for the spectral projections associated to the sublaplacian. So this is more or less the present picture of Ingham and Chernov's theorem. Now we will move on to our main topic of discussion, which is special Hermite and Hermite expansion. So we'll start with their close neighbor, which is the Heisenberg group. So Heisenberg group is basically Cn cross R equipped with the group law, where in the first variable it is just the addition, and then in the second variable, along with the addition, there is a twisting term, which is basically a symplectic form on Rn, R2n. And this twist term actually makes this group a non-commutative group. And this is the simplest example of a nilpotent Lie group, where the Lebesgue measure dz dt, the 2n plus 1 dimensional Lebesgue measure, plays the role of Haar measure. The group Fourier transform of an integrable function on the Heisenberg group is an operator valued function, which is defined on the non-zero reals and defined by integrating the function against this pi lambda, where these pi lambdas are the Schrodinger representation of the Heisenberg group. To be more precise, these pi lambdas are the infinite dimensional irreducible unitary representations of the Heisenberg group, which are non-trivial on the center, and they are realized on the Hilbert space L2Rn and defined by this formula. This is just translating the function first and then multiply with some oscillatory factors. And up to an equivalence for any infinite dimensional unitary irreducible representation on the Heisenberg group, which are non-trivial on the center, they are equivalent to pi lambda, one of the pi lambdas. Now we will be, throughout this talk, we will be using this notation. Pi lambda z0 will be denoted simply by pi lambda z, and when lambda equals to 1, we will just call it pi z. In fact, these pi z's are basically projective representations of Cn. Okay, now we'll define the Weyl transform. So given an integrable function, the Weyl transform of that function is defined by integrating the function with respect to the pi lambda z. And for lambda equals to 1, this is, we will call it Wf. and these are all bounded operator on L2. And the group Fourier transform and Weyl transform are very related, because if we consider a function on the Heisenberg group and take the inverse Fourier transform on the central variable and then take the Weyl transform of that function, then we will recover the Fourier transform, group Fourier transform on the Heisenberg. So actually we are mainly interested in the spectral decomposition of the operator that we are talking about. So we'll start with that. So the sublaplacian on the Heisenberg group is explicitly given by this formula. So in fact, these are actually, so the sublaplacian is actually sum of squares of certain vector fields on the Heisenberg group. Not all the vector fields, we will be just excluding the vector field corresponding to the central variable. And Hermite and special Hermite operators are related to this sublaplacian. So if I consider a function on Cn, suppose f is a function on Cn, we multiply it with e to the power it, then it becomes a function on the Heisenberg group. Now, if I apply the sublaplacian, then you can see that this it is an eigenfunction of ddt and also d2 dt square. So that it will come out, then whatever is left that will be applied on the function on the Cn, and that is called the special Hermite operator. And if we consider the Weyl transform of special Hermite operator applied to some function on Cn, that will give us here the Hermite operator. So they can be calculated explicitly, and the explicit expressions are this. So obviously from the expression it is clear that they all are elliptic operators. Now we are interested in the spectral decomposition of those operators. So actually to pose the problem, we need to first study the spectral decomposition. I mean, what is the spectral projection means and all these things. So for that I will need some notations. So I will develop this notation first. So we'll start with Hermite functions. So Hermite functions are basically some polynomial times Gaussian, where these HKs are the Hermite polynomials, and this constant factor is multiplied to make these functions, make the L2 norm of the function 1. And we know that this forms an orthonormal basis for the Hilbert space L2R. On Rn, the multidimensional Hermite functions are just defined by taking the tensor product of one-dimensional Hermite functions. And also they forms a basis, orthonormal basis for the L2 Rn. And they are eigenfunctions of the Hermite operator with eigenvalue 2 mod alpha plus n. So I will come back to it later, but for the time being, I just need Hermite functions to define special Hermite functions. So once we have Hermite functions, the special Hermite functions are defined as the matrix coefficient of the projective representation pi, which is basically defined by this inner product. So here alpha and beta are varies over the multidimensional natural number. And if you follow the blue color, then this is exactly the definition of this representation pi z, and these special Hermite functions are explicitly given by this formula. And it is known that these are actually eigenfunctions of the special Hermite operator with eigenvalue 2 mod alpha plus n. And this function forms an orthonormal basis for the Hilbert space L2Cn. So using the basic Hilbert space theory, if I have a L2 function, I can expand this function in terms of this orthonormal basis. Now to get a compact picture of this expansion, I will write the sum into 3 different parts. And then we will use the Lagrange functions. Here we can see the interplay of special functions in harmonic analysis. So Lagrange functions are defined by this formula, where ln minus 1k is the Lagrange polynomial and multiplied with the Gaussian factor. And here we are multiplying with this constant. This is some sort of a normalizing constant, which makes this which make the value of this function 1 at 0. Now using this Lagrange function, we can actually calculate the terms in red explicitly in a more compact picture, and it is known that that thing is actually given by 2 pi power minus n times the twisted convolution of the function with the Lagrange function. And the twisted convolution is defined by this formula, where you take f of z minus w, multiply with zw, and then instead of integrating with W, we will just multiplying with the oscillatory term, the twisting factor, and then integrate, because if the twisting factor is not there, this is basically the convolution. That's why it is called twisted convolution. So once we have these things, using the Hilbert space theory, the spectral decomposition of a function using the special Hermite operator takes this compact form. The function can be, where the series is convergent in L2, and using the Parseval identity reads as this, where the L2 norm is given by these norms of these guys, F cross Lagor function, and these are actually eigenfunctions of the special Hermite operator with eigenvalue 2k plus n. And if you notice, here, so all these things add up to this twisted convolution with Lagor function, and these are eigenfunctions, and this eigenspace is actually an infinite dimensional eigenspace, and with eigenvalue of the eigenspace is 1, and this f going to f cross Lagor function is the spectral projections associated to the Laplace associated to the special Hermite operator. So once we have these things, we can ask the following question. So if f is a non-trivial function vanishing on an open set, what would be the best possible decay of the L2 norm of the spectral projections as a function of the eigenvalue? So this is the main question we will be talking about. Now you can see, as in the Euclidean case, any kind of exponential decay is ruled out, because if the spectral projection has this kind of exponential decay, where remember 2k plus n was the eigenvalue, then one can prove that using some calculations, one can prove that then the L2 norm of the special Hermite operator, take the power m, apply to f, that norm is, the growth of the norm is restricted by this factor, which is c to the power m plus 1 times 2m factorial. C is a constant independent of this m, which is true for every m. Now we can use the famous regularity theorem of Kotake and Narasimha, which says if omega is an open subset of Rn and P is an elliptic operator of order k with real analytic coefficients. Suppose U is a function which satisfies this inequality, where this k is coming from the order, then the function is real analytic. So we have, using that exponential decay, we have exactly same inequality, but this is true for any open set subset omega. So in particular, we are taking Cn here, Cn which is R2n. So 2 is because the special Hermite operator is elliptic operator of order 2. So now using Kotake and Narasimha's theorem, we can say that f is real analytic. Now f is real analytic, but if f vanishes on an open set, then f is 0. F will be 0. So we can just see that, just as in the case of Euclidean space, any kind of exponential decay is ruled out. So we can ask here similar questions. Is it possible to arrive at the similar conclusion with slower decay than exponential, or what would be the best possible decay? So we are heading towards actually the Ingham type theorem for this spectral projections associated to special Hermite operator. But to tackle those type of problems, we need to equip with so many weapons. So one of our weapon will be Chernoff type theorem. So we will first consider Chernoff type theorem for the radial part of the special Hermite operator, which is given by this L0. I am denoting this by L0, and this is known as the Lagor operator. So to consider the Chernoff type theorem for the Lagor operator, we need to understand the expansion associated to the Lagor operator. So let me just recall few things about that. So Lagor functions on the half line, we defined it by psi n minus 1 k r. This is again the same definition. This is the Lagor polynomial times Gaussian, and the constant factor that is multiplied here to make this normalized, so that at 0 it is 1. And we know that these are eigenfunctions of the Laguerre operator with eigenvalue 2k plus n, and this forms an orthonormal basis for the weighted L2 space where the weight is r to the power 2n minus 1. That's a polynomial weight. And since it's an orthonormal basis, we can have so for any L2 function we can have this kind of expansion. So this is orthogonal basis. So we can have expansion where this ck is given by the L2 norm of those function, which can be calculated explicitly, and it turns out to be this. So ck inverse is this. So you can see that ck has at most polynomial growth in k, and f at k is the Laguerre coefficient, which is defined by integrating the function with respect to the weighted measure and against the Laguerre functions. So since it's an orthogonal basis, we can have a Parseval or Plancherel type identity for such expansion. Now, since these are eigenfunction, I can apply the Laguerre operator, the powers of Laguerre operator to f, and take L2 norm, and that will turn out to be lambda k power 2m. Lambda k is the eigenvalue, ck times the coefficient of Laguerre coefficient mod of that square. So this is just basic Hilbert space theory, nothing else. Now, once we have these things, we can prove a Chernoff type theorem for the Laguerre operator. So here is our Chernoff's theorem for the Laguerre operator. So it says if f is a smooth function such that all the powers of the Laguerre operator applied to f is in the weighted L2 space, and they satisfies this Carleman type condition, that is same as the considered by Chernoff, then f cannot vanish in a neighborhood of 0 unless it is identically 0. That means if f vanishes on a neighborhood of 0, then f is identically 0. So on R plus by a neighborhood of 0, function vanishes for R between some 0 to some delta, for some delta positive. Now, to prove this theorem, we will be using a theorem of Carleman. So we will state the Carleman result in the form stated by Digiu for the higher dimensional case. So the result is if mu is a finite Borel measure on R, for which all the moments of the measure are finite. So moment of a measure is mth moment of a measure is defined by this integral. And if we further assume that the moment satisfies this Carleman condition, that is, you take the even moment raised to the power minus 1 by 2m and the series diverges, then polynomials are dense in LP for any finite p bigger or equals to 1. So actually this result was actually by Carleman, then on R, then it was generalized to Rn by Marcel Digiu later. So we will be using this theorem to prove this kind of Chernoff's theorem. And so basically what we need to do is, using the function that is given here, we need to define a measure on R so that that measure will relate the even moment and the powers of Laguerre operator. So in order to do that, I will just present a sketch of proof of the theorem, main ideas mainly. So f is as in the theorem, as in the statement of the theorem. Then we define a measure on R using the Laguerre coefficients. So which is defined by this prescription, that is, it integrates any Borel measurable function phi t dim phi t as the sum. This is ck, and this is the weighted sum of this Laguerre operator, Laguerre coefficients, and take half. So this is defined in such a way that you can see if you take phi of minus t here, then the integral will remain same. That is, the integral is invariant under t going to minus t transform. So that these are called even measure. So this is defined in such a way such that this mu f is an even measure on R. Now one can check that this measure, since f all the Laguerre operator applied to f is in L2, weighted L2, then one can check that this actually defines a finite Borel measure on R. So once we have this definition, we can easily calculate the even moments. So see, since it's an even measure, so all the odd moment will be automatically 0. So we don't need to care about the odd moment. So
this is
just
due to Come back to the previous slide.
Yeah.
This is due to the fact that pi root lambda and minus lambda there. That is
Yeah, exactly. Because
okay.
we constructed in such a way so that this measure become
So
even.
it is
So we will be
symmetric.
using that in the proof later.
Okay, yes.
So the even moment can be calculated explicitly, and that will turn out to be this lambda k power m. Remember, we were working with lambda k root, so root over lambda k. So I will just only have lambda k power m, ck, and the Lagrange coefficient. And actually, those measures are supported on the spectrum of the Lagrange operator. So once we have this, we want to estimate this even moments in terms of the powers of L2 norm of the powers of Lagrange operator. So we can just write lambda k power m to be as lambda k power m minus j times lambda k power m plus j times lambda k power minus j, and then apply Cauchy-Schwarz inequality. Then we will get this. This is just to get a square in this Lagrange coefficient. And this j I can choose large enough so that this Cj is a finite constant. That is possible because lambda k's are polynomials in k, just linear in k, and ck's at most have polynomial growth in k. So now once we have this, we can use the hypothesis. So one can show that the Kerr-Lehmann condition on the Lagrange operator side, that will imply the Kerr-Lehmann condition on the moment side. So the even moments will satisfy the Kerr-Lehmann condition, and as a result, the polynomials will be dense in LP, but in our proof, we only need it for L1. And since it's an even measure, one can show that even polynomials will be dense in even L1 functions. So that is very important. Now we will use the vanishing condition. So the vanishing condition, again, using the Lagrange expansion, I can just apply the Lagrange operator term by term here. Since these are the eigenfunctions of the Lagrange operator, so lambda k power m will come out. Now, using the vanishing condition, that is f vanishes on a neighborhood of 0, then as r tends to 0, all these things will be 0 for every m. Now, if I apply this here, and since we have normalized our Lagrange function such that at 0 it is 1, we can get this. And this is true for every m. That basically implies that for any even polynomial, this expression is 0. This is directly from this expression, and which, along with the fact that even polynomials are dense in the even function, will show that f is 0. So this actually proves the theorem. And if you see the proof, you can see that the full power of the vanishing condition that we have assumed is not needed here. Just if we just assume this one, that all the powers of the Lagrange operator applied to f, that
Can you
is
explain
going
this third point?
Sorry.
Third point you explain once more. That
So
okay.
If you take any even polynomial,
Yes.
Even polynomial will be a function of t square, right?
Yes. Yeah.
So even polynomial will be a function of t square. So that will be a sum of lambda k powers of lambda k, right? Because
yes.
I'm taking root. So from this, and this is true for every m. So this will be a sum of lambda k power m's. So that will be 0. And then there are some steps are there which I am skipping just to give you the main idea. So then one can show that then if since even polynomials are dense in the even functions in L2, in L1, we can show that f is 0. These two conditions will show this. So this actually proves the analog of Chernov's theorem for Lagrange operator. Now once we have this, we can move to proving a Chernov's theorem for the special Hermite operator. So this is the theory statement. So if f is a smooth function such that all the powers of special Hermite operator applied to f is in L2, and it satisfies the Kerr-Lehmann condition, then f cannot vanish on any open set unless it is identically 0. That is, if vanishes on an open set, it will be identically 0. Now our main idea is to idea is to reduce the case to a radial function, then use the result for the Lagrange operator. Now to reduce this case to a radial function, we will use twisted spherical means, which is defined by F twisted convolution with the mu r, where mu r is the normalized surface measure on the sphere of radius r in Cn, and which is defined by this formula here, z minus omega, then this twisting factor is there. So we will use this twisted spherical mean to reduce the problem to a radial problem. And then we will use Lagrange operator, the result on the Lagrange operator. Now, the relevant fact, the most important fact about the twisted spherical means, which is relevant for us, is that the twisted spherical means has an expansion in terms of Lagrange functions. So this expansion is there, and from this expansion, it is clear that if I consider f cross mu r z, fixing z as a function of r, then the Lagrange coefficient will be the spectral projections of the function we are considering. The function we are considering the spectral projections associated to the special Hermite operator. So that will be the main fact we will be using. So now if we fix a point, so suppose f vanishes on an open set V, then and we consider this function f cross mu r as a function of r, then from this expression it is clear that then fz, which you denoted by fz, that will be vanishes for a small interval for small around delta. That delta will depend on z for any r between 0 and delta. And then we can use that fact that f is a projection. F going to f cross the Lagrange function is a projection, that is this will be same as this, and then here we can apply the Cauchy-Schwarz inequality to get the L2 norms. So once we have this, then we can since it's a function on the half line, we can apply the Lagrange operator, and using the expansion of Lagrange operator, that will turn out to be equal to this, where these are the Lagrange coefficient that is coming in terms of the spectral projections. Now we use this inequality, that is this is dominated by the L2 norm of the projections. To use that, then we can estimate that in terms of the special Hermite operator. Now the Carleman condition on the special Hermite operator will imply a Lagrange operator. But for the Lagrange operator, we already have a Chernoff theorem. So using that, we can show that fz are 0. Fz are 0, fixing z. Now, since fz are 0, its Lagrange coefficient also will be 0. And that is true for any z in that open set V. So we have the spectral projections are 0 for only spectral projection are 0 on the set V. But spectral projections are the eigenfunctions of an elliptic operator, which is special Hermite operator. And we know that from the elliptic regularity theorem, we know that eigenfunctions of the special elliptic operators are real analytic. So since it is real analytic and vanishes on an open set, so spectral projections will be identically 0. And since this is true for any k, so we conclude that f is 0. So this actually proves the result of Chernoff's analog of Chernoff's theorem for the special Hermite operator. Now we will move to Ingham type uncertainty principle for special Hermite projection. So first we will talk about the example that we have constructed. The example is for the special Hermite expansion is actually deduced from the example that we have constructed for the Heisenberg group. So I will first describe that. So this is in a joint work with Bakchi, Sarkar, and Thangavelu. So assume that theta is a positive decreasing function on the half line which vanishes at infinity, and the integral, this integral is finite, that is theta is integrable with respect to t inverse dt. Then we can construct a compactly supported smooth radial function on the Heisenberg group whose Fourier transform satisfies the estimate. So Fourier transform is a bounded operator, and f lambda star, f lambda will be a non-negative operator. So we can talk about positivity of that operator. So this operator is decays like this. So the meaning of this expression will be clear in a moment. And h lambda is a scaled Hermite operator. So the proof is very non-trivial and technical, so I don't want to bore you giving the proof. So I will just tell you what the function we have constructed, and the function is very nice. So we take balls. So we first take balls on Cn and take the characteristic function of the balls, and then on the central side, on the central variable, we take open interval and then take the characteristic function of the open interval, and then we take the tensor product of these two functions. That will give me a function on the Heisenberg group. Then we take infinite convolution of these functions. That is f1 convolve with f. This is Heisenberg convolution. Heisenberg convolution. So one can show that this infinite convolution actually makes sense as a L2 and also as a L1 function, and then so that we can calculate the Fourier transform of this function explicitly. And since it's a radial function on the Heisenberg radial function, that is, it depends only on the Mordjet variable. So with the Fourier transform can be calculated explicitly, where pk lambdas are the Hermite projections, scaled Hermite projections, and these are actually Laguerre coefficient, but anyway, so these are the coefficients, basically the eigenvalues of the operator. And this expression now basically means that these eigenvalues are dominated by this Ingham type decay. So once we have this example, we can construct an example for this spectral projections associated to special Hermite function. So this is the theorem that we have. So suppose theta is a positive decreasing function vanishing at infinity, and theta is integrable with respect to the measure t inverse dt. Then for any delta greater than 0, we can construct a family of radial functions. I mean, indexed by delta. For any delta, we can construct a radial function g delta, which is supported on the ball. These are balls on Cn. This has some nice properties, that is g delta, f cross g delta converges to f in L1 for any L1 function, two functions. And so this g deltas are basically behaves like an approximate identity, and the spectral projections, L2 norm of the spectral projections will have this Ingham type decay, and where this theta delta will be related to theta, but we can consider it as a different theta, but this theta delta will satisfy the same hypothesis as theta. That is, there will be positive decreasing, vanishing at infinity, and this integral condition will also be there. Now, once we have the example, we can start looking at our uncertainty principle, which is this. So if theta is a positive decreasing function and vanishing at infinity, now suppose the theta is not integrable with respect to the measure t inverse dt, and suppose f an L2 function which has this whose L2 norm of the spectral projections has this Ingham type decay, then if f is vanishes on an open set, then f is 0. Now you can see that since theta is a decreasing function, so this decay is certainly slower than the exponential decay, and this is sort of an analog of Ingham's theorem. But in fact, we can prove better theorem than this. We can actually assume the decay, we can actually assume the pointwise decay only. So theta as in the theta as above, with theta as above. Now suppose f is a L2 function vanishing on an open set, then it cannot have this kind of decay only on the open set. So the important thing is to note that the pointwise decay is assumed only on the open set, which is much weaker than the condition on the L2 norm. So basically, if theta is not integrable with respect to that measure, then if the function has this pointwise decay on the open set only, then the function vanishes identically if it vanishes on an open set. So we'll describe the main ideas of the proof. Now again, we will use twisted spherical means. So that we have already described. So this twisted spherical means, since f vanishes on an open set, so the twisted spherical mean will, as a function of r, will vanish on a neighborhood of 0. Now using the Laguerre expansions, again, we can estimate the powers of Laguerre operator applied to fz, the L2 norm of that. Now this has that pointwise decay. Remember, z is fixed. So no problem. This has that pointwise decay, this one. So this is dominated by this expression. Now, if under the assumption that theta t is bigger or equals to some constant times 1 plus t to the power minus half, so we can exactly, so there is a very tedious calculation. You've seen some tedious calculation. We can prove that this Lagarde operators actually satisfies this Karl-Lehmann condition. Now, once we have the Karl-Lehmann condition, we can, using the Chernoff theorem for the Lagarde operator, we can show that fz is 0. Now, as the same argument works here also, since fz is 0, its Lagarde coefficients will be 0, which are spectral projections, and that is 0 means f is 0. Now, to remove the assumption, to remove this assumption, we will be using the function, we will be using the family of function constructed previously. So in order to, use, in place of f, we will be using f twisted convolution with g delta, because the spectral projections behaves nicely with twisted convolution. So one can show that this f cross g delta, the spherical mean, the twisted spherical mean of f cross g delta will be some some constant multiple of f cross mu r, where these are the Lagarde coefficient of g delta. G delta was a radial function, remember, and the spectral projections. So here I forgot to write a z. So some z will be some point. Here the spectral projections will also have this pointwise decay. And we can choose our theta delta in such a way that theta plus theta delta then will be bigger than some constant times 1 plus t to the power minus half. So using this expression, so you can see f cross mu r is there. So I can consider this as a function of r, and that will also vanish on a neighborhood of 0. And the spectral projections of this has this Ingham type decay with the extra assumption. Now we can apply the previous part of the theorem to conclude that f cross g delta is 0. Then we can take delta to go to 0 to conclude that f is 0. So this completes the proof of Ingham type uncertainty principle for the special Hermite projections. Now we will move our attention to Hermite projections. We already defined the Hermite functions. So these are the Hermite functions. I'm not saying it again. So this phi alpha running over this multidimensional natural numbers, this forms an orthonormal basis for the L2, for the Hilbert space L2. Then every function in L2 has this kind of expansion where the bracket f comma phi alphas are the Hermite coefficient of f, which is defined by integrating the function against the Hermite functions. And now if pk, let pk stand for the orthogonal projection of L2 onto the kth eigenspace of H, which is spanned by phi alpha, such that mod alpha equals to k. Now here the eigenspaces are finite dimensional. Previously for the special Hermite operator, the eigenspaces were infinite dimensional. Here it is finite dimensional, and in terms of the projection, I can write the function this, where the series makes sense on L2, and HF, since PKs are the projections, this will be eigen function of the Hermite operator with eigenvalue 2k plus n. So this gives a explicit spectral decomposition of the Hermite operator. And we want to prove a similar theorem, that is Ingham type theorem, for these spectral projections associated with this Hermite operator. And also we will prove a Chernoff type theorem for the Hermite operator. But in the special Hermite case, we have twisted spherical mean at our disposal, and we use that to and the twisted spherical mean behaves nicely with special Hermite projection, and there, so that we could use that to reduce the matters to a radial function. But for the Hermite case, there is no such thing. There is no spherical means which behaves nicely with Hermite projections. So to compensate that, we will use a relationship between Hermite operator and the Lagarde functions, Hermite functions and the Lagarde functions. And the connection between this Hermite expansion and the Lagarde functions are brought out by considering the Wild transform of the surface measure. Remember, the Wild transform was initially defined for the L1 function, and that naturally extends to naturally can be defined for any finite measure. and mu r is the surface measure for the sphere of radius r. So we have this kind of expression where, so this is a bounded operator and we have the spectral decomposition. So pk's are the spectral projections and the coefficients are given by Lagrange function. Here this Hermite expansion and Lagrange functions are related. Now the explicit expression for this, sorry. Hello.
Yeah, I think you can carry on. Someone just unmuted themselves. Yeah.
Okay, thank you. So now suppose f is an L2 function, we can instead of previously we were taking twisted spherical means. Instead of taking twisted spherical mean, we will apply the Wild transform of the spherical measure to f. That will have this kind of expression, and from this expression it is clear that if f vanishes on a ball, so for example if vanishes on an open set, then if I take xi from a smaller ball, that is if I take xi from a smaller open set, then we can show that from this expression it is clear that as a function of r, this Wild transform of measure applied to f vanishes on this neighborhood of 0. So this will make use, and this has a very, using this expression, using above expression, we have this kind of Lagrange expansion where the coefficient is the given, where the coefficient are given by the Hermite projections. Now we are in the same setting, similar setting as the special Hermite operator. We have a function which vanishes on a neighborhood of 0 and which has a expansion in terms of Lagrange function, but one little change is here the Lagrange coefficients are Hermite projections, and since it's a Hermite projection, so we can apply the Lagrange operator here. Lagrange operator, it will come here, and since these are eigenfunctions of the Lagrange operator, so 2k plus n, powers of 2k plus n will be there. We can consider the powers of 2k plus n with these projections and get this expression. So this expression valid if for every m powers of Hermite operator are in L2. Now once we have where L, remember that L0 was the Lagrange operator. Now once we have this expression, we can just now relate the Kerr-Lehmann condition of the Hermite operator with the Kerr-Lehmann condition of the Lagrange operator. So we can prove a Chernoff type theorem using this expression. So Chernoff theorem for the Hermite operator says f is a smooth function such that all the powers of Hermite operator is in L2 and it satisfies the Kerr-Lehmann condition. Then if it cannot vanish on an open set unless it is identically 0. Now to finish with the Chernoff theorem, so before finishing with the Chernoff's theorem, I just want to mention that recently we found a more sharper result, in the sense that we found the Chernoff's theorem for the Hermite and special Hermite operator where the vanishing condition is weaker, that is if vanishes on a single point 0, then it will happen. It's sort of a genuine analog of Chernoff theorem for this. Okay. Now we will, once we have these things, we can prove Ingham type uncertainty principle for the spectral projections where theta is as in the previous theorem and theta is non-integrable with respect to this measure. Now if f is an L2 function, and then it cannot have this, then the spectral projection cannot have this pointwise decay. And you can see that this is obviously slower than exponential decay, but we cannot use twisted spherical mean. So we will be using the same thing, the Wild transform of the measure applied to the function. So under the assumption that under this assumption, using this function, we can show that f is 0 using the Chernoff theorem for Lagrange operator. Now to remove the assumption, previously for the on the Euclidean case or the Riemannian symmetric space case or the special Hermite case, we are considering functions constructed for those spaces. I mean for spaces, I mean we consider the functions g delta, which were constructed for the whose special Hermite projections have nice decay. But here we don't need to construct such functions. We can use the function constructed for the on Cn. We can just take the Weyl transform of that and then apply to the f that we are working with. So we can have a family of function f delta. So the explicit expression of this f delta is this, and we can show that this f delta xi actually vanishes on a smaller open set. And we can apply whatever we did for this, and we can show that this spectral projections of this f delta will be decaying like this kind of decay with theta replaced by theta plus theta delta, and that will be bigger than or equals to some constant times 1 plus t to the power minus half. And then we can use the previous part to conclude that that is 0. And since g deltas are going to, so these deltas are sort of g deltas are sort of approximate identity. So Weyl transform of g delta that can be proved to be go to identity, and so f delta will go to f as delta tends to 0. So this completes the proof of Hermite uncertainty principle for Hermite projections. Now, since PKs are projection, we can use the pointwise from the pointwise version. We can prove an L2 version, which says if theta is a positive decreasing function vanishing at infinity and theta is non-integrable with respect to the measure t inverse dt, then f is an L2 function which satisfies whose L2 norm of the spectral projection satisfies Ingham type decay. Then if f vanishes on an open set, f will be 0. And also all these theorems are sharp in the sense that we can actually construct a function. So when the theta is integrable with respect to that measure, we can actually construct a compactly supported continuous function on Rn whose spectral projections, Hermite spectral projections, L2 norm of that will have this kind of decay. This will not be used in the proof, but for the sake of sharpness, we have this theorem. So this is all. These are all. So these are the references. So this is the classical paper of Ingham, and this is the classical paper of Chernow, and the talk is based on this paper. And also similar results are done for the rank 1 compact symmetric spaces. If anyone is interested, one can look at this paper. Thank you.
Thank you for a really nice talk. So are there any questions? Okay, I don't know. I have a small question.
Yeah.
So here you are talking about a Hermite operator, right?
Yes.
So have you, I mean, do you know anything if you replace that mod x square by a positive potential? Are there any results known?
No, so you see the explicit spectral decomposition for the operator is used. So we need to know the explicit eigenvalue and the eigenfunctions.
For all, like for
Yeah.
all whatever index.
For whatever we did for special Hermite operator and for the Hermite operator. So if we don't have that, this method will not work.
Okay, okay. But yeah, one can think of some other method.
Yeah, one can think of, there is no harm in thinking.
Mm-hmm. And also, I'm not an expert on uncertainty principles, but there are also uncertainty principles related with the Schrödinger solution of the Schrödinger equation, right?
Yeah, yeah. Actually, this Ingham type uncertainty principle also gives unique continuation property for the Schrödinger solution of the Schrödinger operator, Schrödinger equation.
Mm-hmm.
It is proved on Rn or on R by Luis Vega and his team. Then on Rn, this Bhomik Ray Sen, they proved similar results on Rn and on complex semi-simple group. It is also there in Riemannian symmetric space of non-compact type, but we don't have such theorems for Hermite, special Hermite, or on the Heisenberg group, because the solution of the Schrödinger equation and Fourier transform is very related for Euclidean space. But in case of Heisenberg group or Hermite operator and special Hermite operator, there is no such relation.
Okay. Are there any more questions? Okay, if not,